So what I want to do is walk through what I think the story of MAVEN is, and the story we can tell today in terms of understanding the history of the atmosphere. So I'm going to touch on all of the results to try to weave them into a story from end to end. But pretty much everything I say, Dave, and Paul is going to talk about in more detail. So I'm going to try to give you the overview from end to end and let them fill in the gaps. But first I wanted to talk about the status of the mission. We went through the history last night, so I'm not going to go through the first part. We're about 7 months into our One Earth Year primary mission. And with the instruments that we have on MAVEN, they are not straightforward instruments where you just take a picture and look at it and get the results. They require a lot of analysis and calibration to understand what you're seeing. And that's why it's taken 7 months to put together our first story of what we're seeing. We've put out some bits and pieces, but this is really the first chance we've had to try to weave it into a story. We're also in the middle of writing up our first round of papers for publication. Those are being submitted over the next couple of weeks and will come out hopefully not too long after that. And based on what we're seeing, we're certainly on track to achieve the science results we set out to answer the science questions. That's really important for us in terms of getting out of the mission what we had intended to get out of it, and also for NASA because that means that sometime over the next number of months, we hope they'll be able to declare victory and success with MAVEN. And most importantly, it means that since we're on track, they've now given us approval for a 1-year extended mission. This was decided just this past week, and along with some of the results I'll be talking about today, it's going out as a web release, web feature that's being posted this morning. So that's the official announcement. The extended mission, it's a little bit odd. Normally they do it 2 years at a time through the process that they call senior review, where they look at all the missions. They did that for Planetary last year. We hadn't gotten to Mars yet, so we weren't part of that review. But with our mission, 1-year primary mission end coming up, they had to do something. So what they've done is, in response to a proposal we submitted, they've extended the mission for 10 months, 10 and a half months. That gets it in sync with the senior review process. So we get to turn around in a few months and start it all over again, Dave and Dave. I know Dave especially is really excited about that. That's better than the alternative. I'm really delighted that we're able to continue with the observations. What I want to do is first give you the context of MAVEN as a mission, and then come back and tell you about some of the results we're getting. I think people in this room know the difference between Earth and Mars. I don't need to have the labels up there even for you to get it right. Mars is about 1.5 times as far from the sun as the Earth is. It's got an atmosphere a little less than 1% as thick, so it's a lot colder. Liquid water is not stable at the surface today. It would either freeze or evaporate or sublimate or all of the above. Yet despite that, there's a lot of evidence for liquid water having played a role, even recently, on the surface. To my mind, and in the minds of a lot of people, the overarching question, scientific and philosophical question for Mars is, did it ever have life? And if it did, could there be life today? The reason this is an interesting question is that we see that Mars has all of the ingredients that you would think necessary to support life. Liquid water, if not today, in the past, and if not at the surface, in the subsurface. Access to all of the elements out of which you would build life, carbon, hydrogen, oxygen, nitrogen, etc. There are a couple of dozen that are used on Earth. And then a source of energy that can drive metabolism. On Mars, a lot of the energy could come from chemical reactions between water and rock. That drives some life on Earth and is thought to have been the driver of some of the earliest life on Earth. The fact that Mars has these all, and that we think this is really all the ingredients you need, says that it's not a stupid question to ask whether there could have been life on Mars. If Mars, and my view of the Mars exploration program is that it's really focused on that question of whether there was life. The goal of the future program is to bring back samples to answer the question, to try to answer that question about life. If Mars ever did have life, the questions become how did it interact with its planetary environment, and why did the environment change on Mars from one that seemed suitable to being able to support life to one that isn't suitable to supporting life, at least at the surface today. That is, the questions that I've posed here are the ones that lead me directly into MAVEN, trying to understand the climate and volatile context of whether there was life on Mars. The pictures I have here, it's the Allen Hills meteorite on the left and a photomicrograph, electron microscope image of something that was originally interpreted as a possible fossil microbe in that rock. I think most people today accept the view that this rock does not tell us about possible life on Mars. It's been too heavily contaminated by terrestrial environment and organisms, and by processing that led to images like this. What we need to do is to bring back samples that have been unadulterated, uncontaminated, and look at them in terrestrial labs. And that's the way we're going to answer this question. In the context of climate, though, we have a lot of evidence for ancient water having existed on Mars. I picked just one very well-known image showing these branching river systems, valley networks that look like water flowed through them. I think that these are very common. I think it's very widely accepted that these were carved by water because there's really no other liquid that could do it, and because there's so much evidence for water on Mars. We certainly see it from the Curiosity, from the Opportunity and Spirit rovers, a lot of evidence for liquid water, a lot of evidence for changing liquid water over time. We see these on the ancient surfaces, but not on younger surfaces, which says that something changed in Mars history so that it went from an environment able to support liquid water to one not able to support liquid water, and that requires a change in climate. So we've posed this as the fundamental questions for MAVEN. Where did the water go? Where did the early thick atmosphere go that would have supported, through greenhouse warming, a warmer environment in which liquid water could exist? That was a pretty convoluted sentence, but I hope you guys got the gist of what I was trying to say. And by the way, please interrupt if you have questions. I'd like it to be interactive, and no use, if there's something you want to explore deeper, no use waiting. The question of where did the water go, where did the CO2 go, has two possible answers. It can all go down into the crust and get locked up there. The CO2 is carbonate minerals, water either as ice or as water of hydration in different minerals. And I have a slice through the Allen Hills meteorite here showing these deposits of carbon-bearing minerals that contain carbon that had been in the atmosphere. So we know that some of the CO2 has gone from the atmosphere into the subsurface, but when we do our best inventory of how much, it's inadequate to explain, to have provided enough atmosphere, to have allowed enough greenhouse warming to allow liquid water. Too many word allow, but again, you get the point. The other possibility is all this stuff can go up to the top of the atmosphere where it can be lost to space, stripped away by the solar wind. And I have an image here from the Mars Express spacecraft showing ions that have been stripped away. They've been detected at the present in the Mars environment, in the near-Mars system. And what we don't know from Mars Express is how the processes work to drive the ions, to drive the gas off of the atmosphere into space, or how to extrapolate into how much has been lost over time. And that's really the goal of the MAVEN mission. If you look back over the last 30 years of Mars missions, they've all focused on trying to find the CO2 reservoirs in the crust and to look for what's happened at the surface to answer these questions. MAVEN is the first mission devoted to trying to explore the other half of the question, how much of the gas went to the top and was lost to space. And I have to be very careful because I said MAVEN is the first spacecraft devoted to that. Mars Express and other spacecraft have looked at it. We're not the first to make these measurements, but we're the first to have a full complement of instruments designed to address these questions and devoted solely to understanding the behavior of the upper atmosphere. I want to be careful not to take anything away from what Mars Express and some of the other missions have done. They're spectacular missions, and we're building on the results that they've gotten. So in that context, when we designed MAVEN, we wanted to answer these questions, and we tried to think of all of the processes that we thought could be operating at Mars to drive stuff off. It's usually driven, the processes are driven by the sun and the solar wind through extreme ultraviolet photons, the solar wind and solar energetic particles that come out in storms. All of this stuff drives the physics and chemistry in the upper atmosphere, and through all of these processes that I've listed here can lead to escape. I'm not going to go through these in detail unless you guys want to spend the next 6 hours being really bored by detailed discussion of how each one works. But I will say the blue ones involve neutral particles escaping, the red ones involve ions, and the list of processes is based on analogy with Venus, with Earth, with comets, trying to understand how the physics behaves, what's really going on. The reality is we don't know what's going on at Mars, and we hope we've designed a mission that's robust enough that whatever is going on, we're going to see it, whether it's these processes or other processes. But I do want to pick one in particular and show you how it might work, mainly because I've got a cool video that shows it, simulation. And that's the ability of the solar wind to strip off gas from the atmosphere directly. And this is a simulation done by one of our team members. We're looking where the colors represent the tenuous upper atmosphere. The arrows represent the solar wind streaming by. And you can see the gas just being stripped off. Right there you saw the solar wind intensity double, and the effectiveness of stripping off the gas increase significantly. I think this is one of the major processes that could have been going on. And if you looked at that complex structure, now imagine we're taking one spacecraft on a single orbit every 4.5 hours, passing through it, trying to understand that structure. It's going to take us a year to get the measurements to see what's going on. And in fact, it's going to take, the odds are good that it's going to take longer, that we want to observe through a whole solar cycle. You can see I'm building up toward our next extended mission proposal. The solar cycle is 11 years, and we actually have enough fuel to last 11 years if we're careful about how we use it. And I just hope the instruments and spacecraft will last that long.
Could you do that without interfering with your need to support 2020?
Let me digress now and talk about relay. We have an electrocommunications relay antenna on the spacecraft. That was a requirement by NASA in this mission opportunity. And the reason is to serve as a relay for surface assets. And right now we're the backup communications relay for Curiosity. We're the second backup because MRO is primary, Odyssey is next, and they're both working fine. We're in line after that. InSight will launch in March, I think, and it gets there in September. It gets there 3 days before the end of our first extended mission, so we haven't paid much attention to it. But they have very intense commissioning where it's going to take them a couple of months to get their instruments in place and do everything they need to do. And we're part of that commissioning phase. We haven't really negotiated all the details yet, so I can't tell you how much time we're going to be spending doing relay. What I will tell you is that every time we do a relay pass, it takes us about 1 orbit. And while we're doing a relay pass, we're not doing MAVEN science. And the reason is that the high gain antenna that communicates with the Earth and the Electra antenna that communicates with the surface are both body mounted. So if we do a relay pass, we have to point to Earth, find out what the hell they want us to do, point to the surface, send instructions down to Curiosity or whoever, receive data back, point back to Earth, and downlink the data. And with all that moving around, we can't continue to do the MAVEN science. Some of the instruments can continue to operate, but those that want to be pointed specifically can't. So I will say very clearly, I'm a strong believer in the Mars program. I think we are, although we're a standalone mission, we're part of the broader program, and I think it's our responsibility, as well as our pleasure, to be blunt, to serve as relay, but not to the point that we can't do any science. I think there's a balance between doing science, spending orbits doing MAVEN science, and spending orbits doing relay service. And I would hate to imagine a scenario where we're spending so much time doing relay that we're not doing any MAVEN science. I think they can coexist, and I think they can coexist out through the lifetime of Curiosity, of InSight, of the Mars 2020 mission. But those are all future activities that haven't been negotiated. Did that answer your question?
Yes. Enough for the time being. Yeah.
Okay.
I mean, I can understand that you wouldn't have a full answer without having sort of worked it into your extension and knowing what the full load of the 2020 would be. Yeah, thanks.
So to that point, it would seem that there are now so many spacecraft around Mars and on Mars that maybe the time has come to have a communications infrastructure that's permanent, like launch a satellite whose sole job is like a Tetris, so like just relay signals. Has NASA considered that?
They have, and about I've lost sight of the years, but around a decade plus ago, they were planning the Mars Telecommunications Orbiter to do exactly that. And I think it got lost in the budget shuffle. And at the time, that was before people really appreciated the value of having a relay in orbit. I think the scientists really understand that now and would probably stand behind putting a telecom orbiter in place. Right now, I know it's not in the budget. I mean, they might be able to carve out the money, but it's not part of the plan. And it's not possible to build something, to start today and build something that would be in place for 2020. So I suspect that we're going to become the primary relay for the 2020 mission. And my hope is that we'll be able to continue doing MAVEN science along with that.
Could be a good job for the Russians.
Above my pay grade.
So I know they're still speccing out 2020, but some of the things indicate there may be CubeSats set along for telecommunications. Is it possible to pack enough power into a CubeSat to turn it into a relay?
You've gone beyond my knowledge.
That's what they're doing
InSight's
for
doing
Marco, for InSight. They're launching 2 CubeSats the size of cereal boxes to do EDL, entry descent landing comms relay, so that they don't get in the way too much of PI-led missions.
I think I've read about that. I don't know anything more than what I've read online about the CubeSats. But I believe they will be fully capable spacecraft rather than rather than carrying the connotations that you get when you say the word CubeSat. I think they're just going to be small, full spacecraft. But that's my opinion. So with MAVEN, we designed a spacecraft specifically to address these science objectives. This is the cartoon artist rendition of the spacecraft we've been using. It's reasonably accurate. The high gain antenna for scale is 2 meters across, 37 feet end to end. Kelly, I'm sorry, I'm mixing English and metric, but so be it. I didn't design it or build it, so I'm allowed to do that. The instruments are all accommodated in different places. We have the magnetometers on booms at the end of the solar panels to get them as far away from the bulk of the spacecraft as possible. The Langmuir probe on booms here that look like rabbit ears, and Kelly may be the only one in the room who knows what rabbit ears are, in order to get them away from the electric field and electric potential of the spacecraft. The SWIA instrument, solar wind electron analyzer on a small boom out the back, and 3 instruments on the articulated payload platform, APP, that sits down below the spacecraft. That's 2-axis gimbaled, so it can orient relative to the planet, whatever orientation the spacecraft is in. We have 9 instruments. They were all shown on that last one, but I've grouped them here to show the ones that focus on the sun and the solar wind first. And it may seem surprising that we have 4 instruments on a Mars spacecraft that have the primary responsibility of looking at the sun, but the drivers of the processes are just as important to understand as the consequences of those processes acting, and we need to know what's coming in the form of energy. So we've got a solar wind ion instrument, a solar wind electron, solar energetic particles to look at stuff that comes out in storms, and an extreme ultraviolet detector. This measures all of the energy inputs into the sun. We have 3 instruments that look at ion-related properties and processes, a Langmuir probe and waves instrument, magnetometer, and static, which stands for suprathermal and thermal ion composition experiment. I still think it's goofy to call an instrument static because you want to get rid of the static in an instrument, but I lost that battle. Then we have instruments. I've labeled it neutrals and ions plus evolution. They do a lot of different things. The neutral gas and ion mass spectrometer that Paul will talk about later measures thermal ions and neutrals. The imaging ultraviolet spectrograph. People that know the difference really care about the difference. I don't know the difference. And this looks at ultraviolet, scattered light, and emission from the atmosphere. And this combination of detailed measurements at a point and global remote sensing is a very powerful one. It lets us really understand what's happening at the location of the spacecraft and extrapolate to global properties and processes. The plus evolution means that they measure the isotope ratios, D to H, and all the other isotopes. And this is very powerful for telling us about the history of the atmosphere. I showed this quickly last night just to show you the architecture of the mission. We launched on November 18th at the first opportunity during our 3-week launch period. That is, it was a perfect countdown, no problems, no delays. We launch into orbit around the sun, and we time it so that when we get out to the distance of Mars orbit, Mars is there. When we get there, we're actually ahead of Mars, and it catches up with us. So we approach it from the front side, and we go into orbit with a powered burn of the rocket motors, putting us into a 35-hour orbit. This picture is not to scale. I hope you recognize that. And after half a dozen burns of the rockets, subsequent to that, we're down in a 4.5-hour orbit. This picture is to scale. We're interested in the behavior of the sun, and it matters where we are in the solar cycle. This shows the last 2 solar cycles in terms of sunspot number and where the MAVEN mission is. We're on the declining phase of the solar cycle. That means that we're seeing significant variations. This is also the time period when you get the most and the most intense solar storms. So it's actually the ideal time for us to be in orbit. I'm optimistic that we will now see, we have an extended mission that will go to here. This will take us into the future, hopefully all the way down to solar minimum, where we can see things in a very quiet, undisturbed state, and then maybe back up to solar maximum again. So that's all the background of what we're doing and why. And if there are no other questions now, I'll jump into the science. But let me take a moment.
I had a quick question going back to your, one of your early slides about your nominal mission is 1 Earth year and your extended mission is 10.5 months to get you in sync with the senior review. Was the choice of 1 Earth year as your nominal mission kind of arbitrary? I mean, how long do you need to take measurements to have like what you need? And why did that happen to coincide with 1 Earth year?
You've asked the exact question that the NASA review panels ask. You could propose a 10-year mission, and we all want to survive 10 years, and spacecraft often do, but 10-year mission is expensive. So you've got to balance what's the longest time that we can run versus, and how much do we have to do to get our science versus how much does it cost. And in our case, 1 Earth year was picked because in that time we thought we would see enough variability and enough solar storm events that we would begin to understand the processes going on. Obviously, it doesn't answer all of the questions. There are things that happen on a time scale longer than an Earth year, such as a Mars year. And in fact,
why didn't you propose like a nominal 1 Mars year mission?
It costs more money, and this is a cost-capped mission, and that would have put us over the cost cap. And to get the first answer to the questions we're asking, 1 Earth year we thought was enough. And again, that's the balance between wanting to do all the science you can versus having a limited, focused mission and keeping the cost constrained. There are other consequences, such as in proposing a 1 Earth year mission, we need to have a lifetime of 2 years in space, basically. A year to get there, a year in orbit. If we proposed, and that means all the components have to be qualified for at least that. If we had proposed a 1 Mars year mission, that would have required 3 years in space. You need to justify that the things are going to survive that long more convincingly. If we wanted to go longer, and we said our mission was, say, 3 Earth years, then we would need 4 years in space, and you need to qualify everything for longer. The longer you want to survive, the harder it is to build it to ensure that you'll survive. Because you have to have a real high probability of survival in order to claim that lifetime. The good news is a lot of our components were based on the Mars Reconnaissance Orbiter and Juno spacecraft. Those were both designed with 5-year or longer lifetimes. I forget what Juno was done. I think it was 5-year lifetime in space. So a lot of our components do have a 5-year lifetime, but not all of them. We do have lifetime, limited life items, and they are the likely things to fail first.
Thank you.
Yeah.
So you talked about, last night about how there was the potential for it to be delayed, and today you spoke about how when we're launched right now being kind of the optimum. If it had been delayed, would it have taken more time to collect sufficient data, or would it still be close enough that it wouldn't be?
If it gets delayed, you're delayed by 26 months so that Earth and Mars line up again. And if I back up to that chart here, Earth at launch was here, Mars at launch was up there. You've got to have that orientation in order for the spacecraft and Mars to get out there at the same time. You can make it shorter or longer, but then it requires more fuel or a bigger rocket, and that adds more cost. So the cheapest way to get there is at 26-month intervals, approximately. So if you delay, that's how long you delay. And if you look here, if we had delayed 26 months, our mission would have been much lower on the solar activity scale. It would have been valuable science, but it wouldn't have been the same science. We wouldn't have seen the same solar storm events. But as I said last night, if we had delayed 26 months, we couldn't have even done the mission because we wouldn't have had enough fuel. We would have had enough to get into orbit, and that would have been it. So again, it would have been a very different kind of a mission. We wouldn't have had the precessing orbit and covered the full 3D space, it would have been a longer period, fixed orbit relative to the sun. Still good science, because that was one of our backup positions, but very different mission. You can see we were very motivated to not delay 26 months, not to mention the extra cost. Our estimates were at the time that if we had had to delay, it would have cost something like $175 million just to keep the team for 26 months in order to be able to launch it if problems arose. You need all the people. If you let them go, they go off and get other jobs and won't necessarily come back. And we've seen that with other missions that get delayed. It adds cost. I know MSL was delayed by an opportunity, and that added significant cost.
And Congress wonders why there were cost overruns.
Yeah.
We are very proud, since you mentioned that, of the fact that we underran our budget. We came in $64 million under our life cycle cost, and that's 9.8%. The drivers were that we had no technology development, that we stayed on schedule, and the mission we set out to do in our original proposal is what we did. We didn't start adding things in the middle, changing requirements, because that's what adds the cost.
I'm sorry, I need to follow that up. You mentioned last night that there was a de-scoping of instruments. Can you talk a little about that?
Yeah. In our original proposal, we had 2 more instruments, and we had planned to go for 1 Mars year. And we realized we were coming in at too high a cost. During Phase A, which was still competitive against another team, we decided we needed to reduce our costs, so we dropped 2 instruments.
Which were?
I'm not going to talk about what we dropped, but I'll tell you a story about that in a second. We dropped 2 instruments. We shortened it from 1 Mars year to 1 Earth year, and we dropped 2 theoretical data analysis investigators. One of them, by the way, was my boss, the lab director at LASP. And if you've ever had to go in and tell your boss you're fired, it's a difficult thing to do. To his credit, although he was not happy, he looked me in the eye and said, "You do what you have to do for your mission, I understand." When we underran our budget, we were able to add him back on, by the way. When we did those D-scopes, we looked at the 2 instruments we dropped, and we realized that we could reconfigure instruments that we had remaining in order to cover the same science. So we did the D-scopes without a change to our science. And we looked at the mission duration a lot more carefully, and that was when we decided that 1 Earth year allowed us to meet our objectives. The way these things work with NASA, if you make changes in your mission that change the science, they'll do a re-review, and they may decide, no, it's not worth it. So it's really important if you take D-scopes that you not change the science. You don't want to trigger a re-review and put yourself at risk. Other questions? So I showed these 2 pictures. I talked about comet sighting spring and the fact that we wanted to see what effect the comet had on the Mars upper atmosphere. So we did as good a job as we could of getting the instruments turned back on after the comet passage in order to see what we would see. And we saw 2 things, both detections of the same phenomenon. Nick Schneider is the head of the imaging ultraviolet spectrograph team, and he says he told his team, now look at the data and see if you can see any differences. And the blue is before, the red is after, and big differences. Even I can see these, and even from the back of the room you can see it. The biggest emission that was coming from the atmosphere in the ultraviolet was this one, which I didn't label, but it's due to magnesium ions. The other ones that have the arrows are, I forget which is which, but magnesium or iron ions. These were ions coming from the dust from the comet. coming in at 56 kilometers per second. It hits the atmosphere, it vaporizes, it heats up enough to ionize, and it created a new ionospheric layer. The mass spectrometer, Paul's instrument, also detected these, and I show here the magnesium and titanium. And I wrote down how many, 11 different metal ions were detected by the mass spectrometer. This was a new layer in the ionosphere created by the comet dust, and it lasted of the order of days. It was formed and disappeared very quickly, but it represented the first detection of metal ions in the Mars atmosphere. Second, the first ever detection of a response of any ionosphere to a specific impact event, a specific event. We see these metal ions on Earth, but they've never seen any change in the layer when a meteor shower occurred. This was a really big meteor shower, and it was at Mars, so we're still trying to understand the differences.
Are you able to extract relative proportions of those ions and determine whether it's chondritic or not?
Paul?
Yes. The relative abundance, when plotted on a log scale, basically reflects cosmic average abundances. The details of the very fine differences, there may be effects of neutralization, differences in neutralization as you get up there and so on. But they all plot on the same cosmic log scale, except for sodium, which is a fair bit higher. And you could imagine that's because it's much more easily ionized form. And I can put that in what I showed you.
Thank you.
So this was detected right after the comet passage. When we did our first deep dip, we lower periapsis for a week at a time in order to see what's there. And that allows us to get the full structure, the full column of the upper atmosphere. And when we did that, we're coming down to a higher density region, and we immediately detected metal ions again. We did it with the static instrument. That blob that's circled is at the mass 55 to 60 range and represents iron ions. And the mass spectrometer, this shows two different isotopes of iron that were detected. Since there wasn't a comet passage at the time of the deep dip, this represents the long-lived layer of metal ions that we think is there all the time from dust coming in all the time. And it represents the first detection of that. So I think this is a real discovery as well. Why metal ions in particular? It's not that they're especially more abundant, as Kelly asked and Paul answered. It's cosmic abundances, but they just happen to be the easiest things to measure when they're present there, and they're the things that you wouldn't expect to be there otherwise. So it's sort of a harbinger of debris.
Before you move on, can you walk us through that upper left plot a little bit? What is straggling, sputtering, background, and it's energy versus AMU, but I'm confused.
I was hoping you wouldn't ask that. Let me try. The instrument I'm going to describe it in horribly oversimplified terms, and Dave, if I get this wrong, please feel free to keep it to yourself. The instrument has an opening, and ions come in, and it uses essentially an electrostatic analyzer and a time of flight detector to measure the energy and the mass. And it does this in all directions, so we can map it out over the sky. So the data is often showed as mass versus energy, where the color then represents the abundance of stuff.
And energy is sort of kinetic energy?
Think of it as velocity,
Yes.
Kinetic energy. So most of this stuff is at thermal energies. So it's ions that are not moving very fast. They're thermal ions. The instrument was designed to measure the really fast ones, and they would show up way over on the right. They're the ones that are escaping, and we'll see this in an upcoming plot. So O2 plus sputtering is oxygen created within the instrument. Background is just general stuff. Straggling, you know, I have no idea what straggling is.
Can I help with that?
If you can do it in a sentence.
Okay, so the way that the time of flight part works is that there's a thin foil. And it's basically you have to have a stopwatch inside the instrument. You need a start and a stop. And passing through a thin foil gives a cloud of electrons, and that forms at the start. And then when it hits the MCP detector, that's the stop. And so passing through this foil, to first order, the ion will go through without any energy loss, and that's the main peak. But some of the ions, as they pass through this foil, lose energy, and when they lose energy, they slow down. And so that's what you mean by straggling, the ones that are slowed down a little bit by the process of starting the stopwatch.
But you need to combine those to get the total abundance. And the stragglers are still part of your sample.
Correct.
The reason I labeled them in this plot was to show that each peak is actually understood by the guy that built the instrument, even if I don't understand them, and that this one that I've circled is a real one. So that's the point that I would want to make out of this plot. Any other questions I can duck?
So how does that compare to Earth's atmosphere? Like, do we?
We're in the middle of working that out. It's the same phenomenon of producing ions from debris, from interplanetary debris or comet dust. It's the same type of a layer, and we're in the process of working out the chemistry of what this does and how it compares to the Earth. We've gotten people that are terrestrial experts involved in this because they've got the models that would help us understand it. So that's, again, ducking your question, but saying it's in process.
Okay, and we still have questions that need answers.
Yeah.
And then if you for my student.
So yesterday you mentioned that during these deep dips you're going down to a few kilograms per cubic kilometer in terms of density. What does that translate to in terms of the number of particles you have entering your aperture here that can then be counted on a plot like this? Are you tens, hundreds, millions?
Depends on the species. I don't have that conversion. It's enough that we can detect the heating of the spacecraft by the impact of the molecules. We can detect the drag. In fact, we use the accelerometers to measure how much it's slowing us down, and we invert that to tell us what the density is at that part of the atmosphere. And in fact, by this summer, we will have done 3 deep dip campaigns, and that will have slowed down the spacecraft enough it reduces the highest altitude, and we need to do a burn to raise that back up in order to stay within our science requirements. So it's definitely a noticeable drag, noticeable effect.
Thank you.
So we had one other set of measurements that tells us about dust, and this is from the Langmuir probe. The Langmuir probe measures electrical potential. And when a dust grain hits the spacecraft, it vaporizes because it's coming in very fast, and that's whatever it hits. And that vaporization and ionization changes the electric potential, and that can be measured. Up in the upper left are different types of signals that are measured. This is in milliseconds, so very short time period. And we see different types of signals depending on what the potential of the spacecraft at the time is. Spacecraft develop an electrical potential. They're charged because they're sitting in space. We've done experiments to see, in the lab, to see what the effect of dust hitting aluminum is, and you get the same sorts of signals. And what we're doing essentially with the Langmuir probe then is detecting dust impacts on the spacecraft, and that tells us there's dust there. This is a
What's the y-axis?
potential of the probe,
Okay.
potential that the spacecraft is measuring, that the instrument is measuring.
I just couldn't read it. That's all.
We're detecting dust. This has been done on other spacecraft. It's well understood. And this shows all the dust hits through midwinter, because I haven't updated my plot, as a function of altitude and solar zenith angle. The gray are places we've made measurements. The colors represent hits. And the key thing is we're detecting dust at an altitude where you didn't expect to see dust. And this represents a significant discovery. We put this out at the Lunar and Planetary Science Conference, so this isn't brand new, but I think it's a really exciting result. What we can't tell is what the source of the dust is. We're hoping that once we fill in all this space and see the three-dimensional distribution, that will give us clues. But the dust can be coming from below. You know, if somehow dust from the atmosphere gets lofted to high altitudes, it can be coming from the moons of Mars, knocked off by impact and moving inward, or it can be interplanetary dust just passing through. But it was a complete surprise to us to find dust at these altitudes. I want to be careful here. I put this picture in because everyone asks me about it, whether this dust is related to the plume that was observed by Earth-based telescopic observers a few years ago and just published in Nature about 5 or 6 months ago. This is a picture of it. You see that bump? It really is a plume. It really does get up to altitudes that MAVEN is sampling. This gets up to 250 kilometers above the surface. And that's an altitude that MAVEN passes through, because we get down to 150 kilometers. And I have no idea whether this is related to it. This was observed one time for 10 days in 2012, I think it was. And I don't understand this plume, because at these altitudes, at the top of that plume, anything should be on, dust atoms should be on ballistic trajectories and should fall out quickly. But this was seen for 10 consecutive days. Same thing here. This stuff should be on ballistic trajectories and should fall out quickly, but we're seeing it there. And my guess is there are charged particle effects, that gravity isn't the only thing acting on this stuff, but it has a charge and it's moving around in response to the electric and magnetic fields. I can't prove that, I can't demonstrate it, but I think it must be the case. I'm sorry, this is nothing to sneeze at.
Can you compare these models to the LADI models of the lunar electrostatic dust charge?
We are looking to do that. The guy that did the lab measurements is the same guy who made the LADI measurements, Mihai Hirani, and he's in our lab at Colorado. So we talk to him regularly, and once we understand this, we're working with him, or getting him to work with us on trying to understand it. He's made a living out of understanding charged particle effects on dust and what it does to the dust, how it moves it around, where you expect to find it, and how you detect it.
Sorry, before we move on. I'm sorry to keep distracting you. I just have these
No,
stream of consciousness.
this is the goal.
So you see this dust concentrated along the day-night terminator?
I have said that, but I'm backing off a little bit on that because we don't understand fully yet the sensitivity.
Okay.
So I would say we see it where we see it, and we don't understand the relationship yet between where we see it and where it actually is.
And have you yet had a chance to probe enough latitude to know whether there's a latitudinal distribution? Because if it's coming from Phobos and Deimos, it should be concentrated near the equator, and how it might get distributed to northern or southern latitudes is making my head hurt.
Charged particle effects do that to my head too, but that's what I would point to. Gravity isn't the only thing. And we should have the data now that answers your question. I haven't seen it. I'm going back tonight because this coming week we have our science team meeting all week in Boulder, and I expect to see some of that data there.
So a simple-minded model might be, the stuff is so fine, yeah, it comes in at the equator, but there's solar wind interactions and it picks up a static charge and gets scrambled.
Maybe. That's the hypothesis I'm putting forward. I have no evidence to back it up, except we certainly see stuff away from the equator. These points are at high latitudes on both the day and the night side.
You're seeing it basically at periapsis, right?
Well, all the way, this is periapsis, but all those colored dots up there, that's up at the highest altitudes in our orbit.
Okay.
This is 100 kilometers altitude, 1,000, and that must be, the highest altitudes are 6,000. So we're seeing it throughout the whole orbit.
And you get any sense of the particle size distribution?
We get no information. All we know is that there's some dust grain that hit us. Yeah.
Where is that located in comparison to like the magnetic? I mean, it's not like magnetic poles, but the
magnetosphere?
Magnetic.
The mini magnetospheres, the magnetic anomalies. These measurements are all in the near periapsis in the northern hemisphere, and the magnetic anomalies are predominantly in the southern hemisphere. Again, we should have data by now. We're starting to get down to the latitude of the magnetic anomalies, but we haven't seen that data yet.
How much charge do you build up on the spacecraft as you dive?
We build up a charge from a couple of reasons. One is when sunlight hits us, it ejects electrons from the metal, photo-emitted electrons, but we also just ram through stuff and accumulate stuff. Typically, we want to stay near plus or minus a couple of volts, but it can get 10 times larger than that. The bigger it gets, the more it impacts our ability to measure the properties of particles that have a charge, because it either brings them in or pushes them away, depending on positive or negative charge. So let me move on to the other cool discovery. And again, we talked about this in Houston in March. So this isn't new, but I do have some new stuff that I'll show in a few minutes that relates to this. And that is the discovery of a diffuse aurora. You may remember Mars Express detected a discrete aurora in the location of these magnetic anomalies where electrons from the sun would come in right at the cusp between magnetized regions and trigger an aurora. We're seeing a diffuse aurora over the entire northern hemisphere that is stimulated by electrons coming in from the sun. The evidence for the aurora, this is what the ultraviolet spectrum in the day side looks like, where the features are triggered by sunlight. On the night side with no aurora, you don't see the same features. If you look carefully, these spikes are different from these spikes because they're coming from different sources. These are coming from carbon monoxide. These from, I can't read that. Is that NO, nitrogen oxide? Nitric oxide? And this one in particular is the most obvious one. You see that band in the night side, and that means there's something stimulating the energetics and triggering the emission. And going in, you would say, well, it's particles coming in from the sun. And in fact, when you look at it, we saw the aurora for 5 days around Christmas last year. This is the size of that feature, the size of the aurora. And it coincided perfectly with the biggest solar electron storm that we had seen up to that time. So we have the cause and the effect of the aurora. Furthermore, when you look at the energy of the electrons coming in and ask how deep into the atmosphere would it penetrate before it's absorbed, and where it's absorbed is where you get the aurora, it goes down into the 50 to 100 kilometer range, which coincides exactly with where the aurora is emitting from. So we have cause and effect. We have the full chain. We're still in the process of trying to understand what the effects of this are, long-term effects of this are on the atmosphere, but it's a new discovery in terms of a widespread process. I have to be careful when I say that, because although we've shown this mapped out over the planet, these are observations from the IEVS instrument, and it observed periapsis by looking off at the limb. And each orbit, it's making measurements at one location. The next orbit, it's the exact same geometry, but the planet has rotated. So we made it on 25 or 30 consecutive orbits, but it's the same geometry, but each time the planet has rotated a little bit under it. So it's all in the same orientation, but it's shown It's shown here mapped out over the planet. We don't know the actual distribution of the aurora. We only know that where we looked, we saw it. So we think it was global and widespread, but we don't know that. And we haven't gotten down to where we would observe the discrete aurora connected to the magnetized regions yet.
Is it a night side aurora, day side aurora, both?
Night side. We wouldn't see it on the day side because it would be lost in the other features.
So it's not direct injection of solar wind into, there has to be some sort of ionosphere distribution to get it to the night
It's
side?
direct injection, but it comes in along open magnetic field lines.
Okay.
You know, if you're used to thinking of the Earth and you draw the magnetic field lines, if you imagine here's the planet, they sort of go like this from pole to pole. On Mars, since it doesn't have a global magnetic field, we have very few closed lines that start at the planet and end at the planet. A lot of them start at the planet and go out and connect up to the solar wind. And the electrons come in along that path. So that can take them around to the night side.
This is not an induced field in the ionosphere or anything like that?
It's going to be a combination of everything. Dave, you're...
So just, wasn't there, I remember reading something a couple of weeks ago, but scientists had only found evidence of aurora in the southern atmosphere or southern hemisphere of Mars?
Mars Express saw the discrete aurora, and it saw it in isolated regions in the southern hemisphere associated with these magnetized regions of the crust. We've seen it in the northern hemisphere globally distributed, not connected to specific geographic regions.
So how did you both find different aurora? And Mars Express made it sound like it only exists in the southern hemisphere because of that magnetized.
They see it where they see it, we see it where we see it. They don't have the sensitivity to see this dimmer aurora, and we haven't gotten down to the southern hemisphere yet to see the discrete aurora. We're trying to build up a picture of all of these processes. And I hate to use the overworn analogy of different blind people looking at the elephant, and they each sense a different part of it when they touch it. But that's what we're doing. We're each looking in different places right now and seeing different aspects of what ultimately is either the same phenomenon or very closely related phenomena. Dave, have I gotten that about right?
Yes. I would add one thing, and that is that this is a rather...
I asked that, Dave. I didn't ask you.
This is a rather unusual event to have an energetic electron population like this, and I don't think a similar event happened for Mars Express. So that's part of the answer as well.
Kate?
Could we just step back into a 101 for a moment on the difference between a diffuse and a discrete aurora, and help me also put that in the context of what I think of when I imagine, the beautiful aurora images that we see on Earth.
Okay. Forget the words diffuse and discrete. We're only using them to try to separate out what Mars Express sees from what we see. The aurora are triggered, in this case, by energetic electrons that come in, hit the atmosphere, and energize atoms or molecules, and then they emit light as they relax.
And this is fluorescence, not ionization.
Dave?
What's that?
It's fluorescence. It's not
Yes.
actually ionizing, it's just exciting.
Yeah, the incident particles come in, collide with the collisional atmosphere. Particles in the atmosphere are excited, and then when they relax back to a ground state, then they emit.
So anytime you have electrons coming in or solar wind particles coming in that hit the atmosphere, it can do this. On Earth, the particles come in and they get trapped in the magnetic field and bounce back and forth between the poles. And if they get enough energy, they penetrate deeply enough that they'll hit the atmospheric gases and stimulate emissions. So you get a polar ring where this happens. On Mars, we don't have a polar field, magnetic field, so they don't bounce around between the poles, but they get trapped on whatever magnetic field lines are there. If we're between two magnetized regions, it can focus them into that little space between them, and you get what we're calling a discrete aurora. If there aren't magnetized regions, the magnetic field lines from the induced magnetosphere just come in everywhere, and it becomes triggered everywhere, and we're calling that a diffuse aurora. Does that help?
Yeah, that
Dave, correct me now.
No, you were great. I was incomplete in what I said before. What I said was correct, but the excitation of atoms and molecules in the atmosphere that results in light being emitted is one of three things that can happen when these particles come crash into the atmosphere. And aurora, if you've ever seen them on Earth, are incredibly beautiful. But at the same time as the particles are crashing in, it can ionize the particles in the atmosphere and create ions. And another thing that can happen is it can heat them, energize them, and maybe give them enough energy to escape or move around differently. So the IUVS aurora are interesting in their own right, but they may also be hallmarks of some of these other things that are happening.
And to elaborate on one aspect of that, we're seeing it in the ultraviolet because that's where we're looking. We think that in addition to the ultraviolet, it stimulates visible light emission, but we're not measuring that, so we can't say anything.
But you could model, because
We
you know
could-
what your species are, CO and CO2, you can actually model what the
And-
emission should be.
Yes, and Nick Schneider says that he thinks an astronaut on the surface would see it at night.
There was just I want to say it was in GRL that just came out from, I think, Jean Lillensten in France, and he and his group, I think, used like a Planetarella to simulate it to the best that they could, and they were saying that, I think, primarily what somebody on the surface of Mars would see, they would see blue light, and then maybe from excitation of CO2, and
Cool.
possibly also some red and greens from oxygen.
I haven't seen that, so I'm interested if you could point me to that. And Laura Aurora wants to comment.
Yeah, just if you ever are reporting on diffuse aurora on Earth, it's going to be a very different process than this diffuse aurora. So you all are using a term that's been used on Earth for a very specific kind of aurora. And the way the process for that type of aurora on Mars, there's no way it could be the same as the diffuse aurora on Earth. Just to let you know, and that's pretty common that words are used for.
So we should come up with a different phrase to avoid confusion.
It would probably help.
Although Davin Larson, a terrestrial auroral scientist, suggested that we use this phrase because of some of the similarities in those exactly.
Yeah, it's just on the diffuse aurora on Earth is mostly due to scattering from particle wave interactions, and I doubt that's what's happening here.
So just as a check, Tom and Laura, I've droned on for about an hour so far, which is what you have allocated, admittedly with questions, and I'm about halfway through my charts. Any issues or concerns? Do I need to speed up, slow down?
Until 10:30.
Okay.
Discussion period, so if we have questions throughout, that's fine.
I think the second half will go more quickly, too. I'll just talk faster. I'll say less. So all of this was just some of the cool things we've seen, but I want to get to the real core, the crux of what MAVEN is trying to measure, and that's the escape of atoms from the atmosphere to space. And I wanted to start with this. This was data, images obtained by the Imaging Ultraviolet Spectrograph on Orbit 1. Again, the spacecraft ops team went to heroic efforts as soon as we went into orbit to get the instrument, the IUVS instrument, turned on quickly to get this data, because these observations were taken at apoapsis from a 35-hour orbit, so at an altitude of around 45,000 kilometers. And almost immediately we were reducing the size of that orbit. So we were never going to get this high again. And we wanted to make these observations, in particular for the hydrogen, looking at ultraviolet light scattered by hydrogen, because that does extend out very far. And it's a little bright in here, but the hydrogen extends all the way out as far as you can see measurements in this image. It's real data. Hydrogen, oxygen, and carbon. There's a red line drawn where the planet is, so you can see that the stuff is actually distributed in a corona above the planet. That's what we expected. Hydrogen, because it's the lightest, is the most extended corona. Oxygen and carbon heavier, so they're closer in. We're seeing the atoms that represent the source of what is being lost. So we're seeing the start of the loss process here.
And the significance of the hydrogen is that this is disassociated water that Mars is never going to get back.
Yes, exactly. So, in fact, that's an important point that the title of the chart says it, but I didn't say it here. Carbon, oxygen, hydrogen represent the components of CO2 and water. And we're seeing them escape as they're broken up by sunlight. So we're seeing the loss of CO2 and water from the atmosphere to space today. By understanding the processes that drive it off today, we can extrapolate to past epochs and learn about how much has been lost over time. And that's the goal of the mission. We're able to use the instruments to map out the interactions of the incoming solar wind with the planet, the creation of a magnetosphere. And we've got the shock wave, termed a bow shock, when that occurs when the solar wind hits an obstacle. The dashed lines represent the bow shock and the magnetosheath boundaries. And these are average values expected based on what we understood. The colors represent MAVEN measurements. And Dave Brain is going to talk a little bit about time variability of this. This is an average picture over the first several months of the mission. What we want to do, though, is to look in detail and see if we can learn something about the escaping species. And here's where it's going to get a little bit difficult, and I want to take a minute to talk about the processes. So don't look too much ahead. When the solar wind comes in, it consists of ionized particles streaming out from the sun. When they hit the ionosphere is, think of it as an individual ion. It's an electrically charged particle sitting in the atmosphere. The solar wind is electrically charged particles that contain a magnetic field embedded within them, moving by it. If you are familiar with electrodynamics, you know that a moving magnetic field creates an electric field. And the way you express that is the electric field is V cross B, velocity crossed with magnetic field. So the solar wind coming in this way creates an electric field that accelerates the ions downward. And if the solar wind is pointed, the magnetic field is pointed the other way, it accelerates them upward. So in fact, there is a discretization of what it can do. It doesn't just strip particles off, it can move them upward or downward with respect to the plane of the solar system. And that's shown in this schematic up here, where you can see not only ions being stripped off and carried down the tail, but some of them being accelerated downward. And we're calling this a polar plume. This was expected based on theoretical models. If you look at it, if you imagine it flipped the other way, it looks sort of like a mohawk haircut.
Mohawk guy.
Haven't you learned you never step on somebody else's joke? That's exactly what I was leading up to, because MSL had their Mohawk guy. MAVEN has the Mohawk planet. See, it would have been funnier had you not said that.
So the polar plume is directing species away in the vectors there are out.
Yes, the stuff is moving down this way. This stuff is lost. It's being stripped away.
And that had been modeled to perhaps exist before you got there.
Yes, and this is one of those simulations. This simulation was done very early well before MAVEN got there. We wanted to look and see if we could identify this polar plume. This is now the MAVEN orbit early in the mission. And you can see that apoapsis, the highest point, was in the southern hemisphere, periapsis in the northern hemisphere. And we're looking for stuff that gets accelerated this way. Remember, it can be accelerated either upward or downward. I'm sorry, I keep doing that. Upward or downward, depending on the magnetic field of the solar wind. So we want to look at times when the magnetic field of the solar wind will drive things downward. This all clear so far? Morgan?
Yeah, so the planet's tilted a little bit. Would we find a concentration of some of those ions on the surface driven down to the surface of one side and concentrations of the other species concentrated on the other pole? Just like on the surface level?
No, this is all taking place in the ionosphere. Anything, say here, that gets driven downward would hit the atmosphere and just become part of the ionosphere or become neutralized. They're just there. It can't go down to the surface because it has to penetrate through so much atmosphere. The stuff that gets accelerated upward from the surface, I'm drawing it downward here, but it's upward from the surface if you're standing on your head there, is lost to space. Is that clear? So we want to look when the plume would be going down this way, and that would require the Y component, trust me on this one, the Y component of the solar wind magnetic field to be negative.
And you're seeing this polar plume when the spacecraft is at apoapsis mostly? Because when it's at periapsis, you're too close? Or
Give me a minute,
okay.
About 3 minutes, and then come back with that question if you still have it. So we're going to look at times when the Y component of the solar wind magnetic field is negative. That's the green line here. And you can see I've circled where it's negative. Actually, I don't have it here. Shannon Curry at Berkeley has circled where it's negative because she did this. And right where it's negative, the static instrument measures all these high energy ions. You can look, these are very high energy, so they are escaping. When you look at them in more detail, this is now the same plot, Kelly, of mass versus energy. And we're seeing very high energy ions at a mass of 16, that's oxygen ions, that are being stripped away from the planet. The energy says these are escaping. So this is, to my mind, a clean detection of this polar plume. So it's the first clean detection that has been made. We can look at it in more detail. And now I'm glad, Kelly, that you asked me about this plot because I want to walk through it a little bit more. This is the same thing. It's mass versus energy. In this case, we're looking at an altitude of 250 kilometers. And I'm going to step up in altitude, but I want to walk through this one first. We're measuring all of the different ions, hydrogen, H2, helium, O+, O2+. And we can now step up in altitude. This is 250 kilometers. These are all at thermal energies. 300 kilometers, 400, 500 kilometers. So this is essentially the same time as that detection of the polar plume. As we move up, we're seeing the stuff get accelerated and being driven away. So we're watching the acceleration into the polar plume.
The energies are actually increasing at higher altitude.
Because the stuff is being accelerated.
Okay.
If I back up to this plot, when the solar wind comes in, it creates an electric field that accelerates things, in this case, to the bottom, to the south. And it continues to accelerate them. So as you get further away from the planet, they would have more energy.
So this represents solar wind pickup and acceleration.
I don't want to use the word pickup here. I would say solar wind acceleration through electric field. So this is an important result because this could be a key player in the escape processes. We're in the process of trying to quantify it as we are all of the escape processes, and we're not there yet. Questions on this? So I've got, I think, one more topic, and that is the effects of solar storms. We've seen a number of solar storm events hit Mars, and I want to walk through one of them a little bit, and that's the March 8th storm. It's complicated because there are actually 3 storms, on the 1st, the 6th, and the 8th. The 8th happens to be the strongest one that we saw the most detail of. Start with the top, which is the extreme ultraviolet energy coming from the sun, and that represents the flare at the sun. And you can see here, this is the March 6th flare. We only caught the declining phase. March 8th, boom, it jumped up in the ultraviolet by what is that, almost 100 times and then declined. And we're interested in seeing what effect that has and what effect the solar storm has. We see the flare when the sun emits the storm, and then not much longer after that, we see the solar energetic particles, the coronal mass ejection, all the stuff that was sent out in the storm. And Dave, did you tell me you've got the Enlil model that shows that? Yes. So you'll see that a little bit more graphically when Dave talks. But we see the storm, the particles get to Mars after that. This is the energy level as a function of time, and the color represents how many particles there are. And we're interested in tracking that through. If we look in more detail, here's the solar energetic particles. They carry with it magnetic field, and you can see this big jump in the magnetic field. If you look at the solar wind pressure, that's an indication of what you're seeing hit you. We actually measure the density and the velocity and combine them to get the pressure. That's this one, and that March 8th event, up to that time, was the strongest solar wind pressure we had seen. So we're clearly seeing a big storm hit Mars. And part of the answer to your earlier question, Kelly, was we designed a one-year mission to be sure we'd see at least one, if not more, really nice storms. So we've done that within our year.
I just want to make sure I understand the terminology you're using. SEPs, are these the relativistic particles that are ejected from the solar flare as opposed to the stuff that's in the high-speed coronal mass ejection?
I think the latter.
Okay.
So what does this do at Mars? The first thing it does is it triggers another aurora. And this is the same plot I showed you earlier of the aurora, but now this is the 5-day thing we saw around Christmas. This is the whole history of aurora that we've seen, and we saw the March 3rd and the March 8th events. So all these energetic particles come in and trigger a new aurora. And it triggers a dramatic increase in pickup oxygen, which is oxygen being stripped away. And I'm not going to walk through this in detail because it would take me longer than I want to spend, but you can see the increase in the red stuff. That's oxygen being stripped away as pickup ions, being grabbed by the solar wind.
O+.
Yeah. And I want to show a little bit more. This is the planet before the coronal mass ejection hits, and we're looking at a bunch of things plotted as a function of time. The bottom one is the altitude of the spacecraft, and I've marked periapsis, so we're seeing through one orbit, more or less. The top one is the crustal magnetic field, and at periapsis we're sensing these crustal fields, and I just marked it here so you would not pay too much attention to that stuff, to stuff that occurs at that time. What are we seeing elsewhere? I've got static measurements, SWIA and SWIA. the SWIA measurements, we're seeing solar wind protons. I keep walking back and forth and having to reorient myself. These are the solar wind protons coming in, where we're detecting the solar wind directly. At the same energy level, we're seeing solar wind that has penetrated deep into the, deep through the ionosphere and into the region below the ionosphere. And we think it does that through a series of charge exchanges. Turns it neutral so it can penetrate, turns it back to charge. But just pay attention there. And let's see, in the static measurements, we're seeing the solar wind. This is the energy level, and this stripe is at the mass of the solar wind. And we're seeing oxygen ions here, this colored blip, that are escaping. And now watch what happens when, this is before the CME, when we switch to looking at the orbit that includes the CME. Again, periapsis, crustal fields. We see a dramatic increase in the penetrating solar wind, a dramatic increase in the upstream solar wind, and a dramatic increase in the escaping stuff. So we think that the storm is driving escape at an enhanced rate. Let me flip back and forth, and you can just look at those areas and see the changes. For example, the penetrating solar wind and the solar wind. You can see how big a difference that is. The escaping oxygen, O and O2. You can see the change induced there. We're in the process of determining from the observations what the change in the escape rate is. So I don't have that, but we have modeled it. And the models suggest that during these events, we should be seeing a 5 to 10 times increase in the escape rate. And when you look at stuff like this, you can believe that. I mean, you can believe it's a plausible number. So we think that the storms may represent a significant mechanism for loss of the atmosphere. That is, it may be that a lot of the loss occurs during the storms rather than during the times between the storms. Again, one of the goals of MAVEN is to understand each one of those as separate processes so we can extrapolate backwards in time.
May I try to restate what I think you just said? You see escape even in quiet solar wind conditions at some low level.
Yeah.
But you see a 5 to 10 times enhancement during a solar storm.
We see an enhancement. I'm not prepared to say we see a 5 to 10x enhancement. The models suggest that that's what we should see.
Okay. But most of the time, you're in quiet solar wind conditions. So is it fair to say that the bulk of the loss occurs just generally? And yes, you see enhancements when there is a storm, but Mars is losing gas all the time.
Mars is losing gas all the time. It loses it during quiet times. It loses it during the storms. We're trying to quantify each of those, and each of those would extrapolate back into the past in a different way. So I can't tell you yet which one would have been more significant over history, but I think you've got it right in terms of loss today. Keep in mind, this is a really important point, keep in mind that the loss we see occurring today is really important for telling us about how the processes work. It's absolutely negligible in terms of the history of water because the rates were much higher in the past. But we want to study it today because it's really hard to study 4 billion years ago without time travel, and because understanding those processes allows us to extrapolate the processes back in time and see what happened. Yeah.
I know you just kind of touched on today versus back in time, but wouldn't that mean that in times when the sun was a more active star, if these are driving it, that likely, that's, I mean...
That's exactly the extrapolation we want to do. because the history of solar storms is different from the history of the extreme ultraviolet. Both of them drive different sets of processes and different from the history of the solar wind, background solar wind. So we want to understand how each one of those affects it and then extrapolate each one separately back in time. We do have the advantage that we're measuring the isotope ratios, and I don't think we're going to talk about that today because the analysis is still ongoing. But that tells us, I know, I'm disappointed as well, that the isotope ratios will tell us a time-integrated, spatially integrated amount of loss. And that's a really powerful technique. Paul is going to talk a little bit about that from MSL. Are you going to touch on it for MAVEN?
I'll touch on it for MAVEN. I'll also talk a little bit about how you can time travel and get back more than 3 billion years ago with certain things.
Okay, my last topic, and I'm going to touch on this quickly, and Dave is going to talk about it in more detail. This is building up to a story that doesn't have an ending yet. We're in the process of developing that ending. What we want to do is measure the total escape rate from the planet today. That's one of the things we're trying to get. What Dave Brain has done is to draw an imaginary sphere around the planet. This figure shows where the spacecraft has been in that imaginary sphere. The sun is way off in this direction, and everything in the other two directions has been folded into one flat graph. Does that make sense? So it's distance from the sun and distance perpendicular to that, whatever angle it happened to be at. So the spacecraft has visited all of these places that have colors. Every time it passes through this sphere that he's defined, he makes a note of what escaping atoms there are, escaping ions. In three-dimensional space, you know, we have an orbit that's in a plane. It's a very fixed plane. In three-dimensional space, shown now as a function of latitude and longitude around that sphere, we visited a very small fraction of that three-dimensional space. Remember, though, that it's the electric field that controls the escape by driving stuff up or down. And when you consider the changes in the electric field, what that does to this coverage is it turns it into this. So we've actually covered now a significant fraction of the three-dimensional space. And I want to show you the maps of escaping stuff. And this is the same maps that Dave will be showing and talking about in more detail. First, these are all the observations we have. This is whenever the spacecraft passes through that sphere, it's the stuff moving upward and escaping. But you have to take into account that there are some places where stuff is moving downward as well. And that's what he's called the return flux. The geographical distribution is the same of where you have coverage, because at each point you can measure stuff moving up and stuff moving down. And you difference them to get the net escaping flux. And I'm not going to say anything more about this. I'm going to let Dave talk about it in his talk, which will be coming up shortly. Right now, this is not calibrated, so it's in relative flux terms, relative flux units. And I know that Dave has emphasized that by changing the numbers so that you can't convert these to actual number of escaping ions because they're not calibrated yet.
I did it so that I can convert it, so that I won't be tempted to.
Very good. And so that I won't do it. But you can see that there's a lot of structure in here. Over here is coming from the sun. It's, if nothing else, neutrals that turn into ions and are whipped into the planet. You can see the polar plume up at the top, and Dave will talk more about the structure. This is my next to last chart, and I just wanted to put this in here to say that I've talked about MAVEN as a standalone mission. I hope you've gotten the sense from the other things I've said that MAVEN is part of a program. And the program is really to understand Mars as a whole. And to understand something like the history of climate or the history of the potential for life or the possible existence of life, you need to understand a lot of different components of a very complex system. If you're thinking about water, we have measurements from orbit that tell us about water at the surface, measurements from the ground that tell us about water at the surface, measurements from MAVEN that tell us about water that's escaping. We need to understand all these components. InSight, where's InSight? InSight will tell us about the structure of the interior of the planet, which is telling us also about the supply of water from the interior to the surface. And the 2020 rover will pick up samples, I hope, that will eventually be returned to Earth that will tell us about whether there might have been life on the planet. So it's a complex system that you can't explore and answer questions from a single spacecraft. We really need this whole fleet of spacecraft, each one of which addresses different aspects of that system. And I just have a walk-off chart to summarize and say MAVEN is working well. I'm really excited by the results, as you can tell. We're starting to write papers, and we've got exciting stuff coming up in our extended mission, continuing the same observations, but under different conditions of solar wind, solar extreme ultraviolet, the other half of the Mars year. I will stop there, but I'm happy to take more questions.
Great.
And we will make these charts available. I haven't given them to Tom yet, but I will do that this morning, and he'll make them available to everyone. Yeah.
Can you help us get just some context, like general context, as to, based on these results so far, what have you found out now that we didn't know before MAVEN was launched? Like, what is the story of atmospheric changes on Mars? Like, how did MAVEN fill in those holes or change?
I can't give you the complete story because I'm still waiting for that final chapter. I think when we really calibrate the instruments and get the total loss rates, when we learn the total loss rate driven by the solar storm, then we'll be able to write that chapter. When we get the measurements of isotopes in the upper atmosphere, which we have the data, we're in the process of analyzing it, we'll be able to interpret that in terms of loss more precisely than we can today. But what I've tried to do is to show you how we're building this story, going from the energy inputs into the atmosphere to the response of the atmosphere locally to the escape to space. And we've now built up a chain where we have bits and pieces of that entire story. And we can see, we have enough structure that we've built. We can see the house that's going to be built out of it, but we don't have the house finished yet. That's the way I'd put it. The first half of the talk was focused on the things we've actually discovered that were brand new and unexpected. The aurora, the dust at orbital altitudes, and the metal ions from cometary debris. Yeah.
Some of the teams have lamented that solar maximum has made their science not as happy as anticipated. Has your mission had any problems with the sun not being as active as you had hoped?
The sun is what it is, and we're making the measurements we are. If you go back to that plot I showed early on of where we are in the solar cycle, on the current solar cycle, we're at the right place. Would I have liked it to have been a more intense solar cycle? Sure, because that would have been more spectacular. But remember also, we were delayed 2 years. Turns out the solar cycle was delayed about 2 years as well. So we're right at the spot we intended to be, coincidentally, but I'll take that. You measure what's there. And I'm delighted with what we have. The instruments are working well. The spacecraft is working well. The data are just spectacular. And we're pulling out of it what we intended to. So I see every indication that we're being able to address and answer the questions we set out to answer. And to me, that's the important point, not what it could have been had the sun been more intense. We're getting what we wanted to.
I've got a geopolitical question. NASA is notorious for ignoring the accomplishments of spacecraft that it didn't launch. You've got Mars Express and Mars Orbiter mission, the Indian mission, which on paper have experiments that are synergistic, complementary to what you're doing. You designed your mission to be a standalone mission and answer a set of questions inside the box. At what point do you sit down with the Mars Express experimenters and the MAVEN experimenters and pool all your data to get a sum that's greater than the individual parts?
Let me answer the scientific question, but let me answer the geopolitical question first that you didn't quite ask, and that is, I don't know whether NASA is notorious for that. I'm not going to even answer that.
Trust me, it is.
But I'm not going to disagree, but I'm not going to.
Yeah, I'm not going to put it. Debate you there.
I'm not going to put it in my words that you can quote.
Yeah.
The MAVEN team is not notorious for that. We have members of the MAVEN team in this room who are working closely with the Mars Express team and have been for years. We are starting with our science team meeting next week. We are opening up our team meetings to people outside of the MAVEN team who are working with MAVEN data. And that includes a number of Mars Express investigators who will be at our science team meeting. And we're trying to be very sensitive to this issue of we invented it here. We're building on the success of Mars Express. And our goal is to combine our data with their data. I've had many discussions with the Mars Express project scientists, several over the years, about how to collaborate. And we have collaborations that are now beginning to develop. They haven't up until now because the MAVEN team has been so focused on trying to figure out how our instruments are working. We're in the early stages of planning a, I'll call it an upper atmosphere conference for maybe a year from now. That is a real opportunity to bring together not just Mars Express and MAVEN, but the MOM team and all the theoretical investigators and data analyzers out there to try to do exactly what you're asking about. In terms of the MOM team, I've been part of a NASA ISRO Mars working group. And one of the major goals of that is to figure out how to collaborate and how to combine the data sets. So we're having discussions with the MOM investigators, and we're talking, so far we've been talking mainly about coordinating, collecting observations so that we have observations of the same planet at the same time. And next is how to combine the data, how to collaborate on data analysis. So we're very sensitive to that. We don't want to walk all over Mars Express in particular and say we've done things for the first time if we haven't. In my talk today, I hope you've heard all the times I've pointed back to Mars Express and what they did and what we've done that's different or that builds on what they've done. Other questions? Yeah.
One more. So if you could hop in your car with your MAVEN license plate and drive over there and just do a quick little add one more instrument or make a quick little adjustment on the spacecraft to get just a little more data. Realize this is a little bit of imaginary, but what would you throw on there?
I'm not sure. One of the hallmarks of MAVEN from the beginning has been that we designed a good mission to begin with, and we're going to stick with it. We resisted opportunities during development to add on additional instruments. I don't want to name names of instruments, but there were several we gave serious consideration to, And in the end, the overriding factor was, we've got a good mission. If we start adding things on, that's where you rack up the cost increases and the complexity increases. This is all we can handle right now, so I'm not sitting here wishing we had X or Y. We've got a first-rate mission and we're getting the data we wanted.
Can I follow up with that? Does the Langmuir probe and waves instrument give you data on plasma waves that might be coming out of the ionosphere?
What it's designed to measure, and I haven't talked about its main measurements here at all, is the electron density and what's called the electron temperature in the upper atmosphere. Those are important for constraining photochemical processes and solar input into the upper atmosphere and are an important part of the story. It also measures exactly what you said, plasma waves that tell us about processes in the upper atmosphere. So you will see those data start to come out and get analyzed. I haven't talked about it here.
Thank you.
You mentioned sample return.
We're not doing sample return from MAVEN.
But is that something that some people on your science team are looking at for future missions, atmospheric samples?
I'm an incredibly strong believer in the value of sample return. I've been one of the most vocal people, for example, in the last decadal survey that they did for Planetary, in pushing the value of sample return for not just understanding potential for life, but understanding the history of Mars. Sample return involves the solid surface, the gas is trapped within the solid, and gases in the atmosphere. They all tell you something different, and I think it would be just an incredibly powerful scientific result.
So, to follow up on that, could you take a Genesis spacecraft clone and send it through the upper atmosphere of Mars and return it to Earth and get something useful?
Lori Leshin was proposing exactly that mission to return exactly that kind of sample. She called it SKIM. I forget what SKIM stood for. That competed in 2 rounds of Mars Scout, and I know she's still trying to develop the support to fly that mission. So I'm not that familiar with it, so I can't talk about the scientific utility, but I respect Lori tremendously, and if she thinks it has scientific value, I'm sure it does.
I believe Skin, last time I heard, was trying to go through private enterprise.
Was trying what?
To go through private funding versus...
If anybody can get it, Lori can.
Okay, thank you.